All right, let's get right into it. We're going to talk about a massive hidden cost that's buried deep inside the AI industry. It's a problem that hits everyone, from the biggest players all the way down to a two-person startup. And it's an issue that's hiding in the one place nobody thinks to look: the math itself.
Just picture this for a second. Deep inside a Google data center, a server is churning through billions of queries. And at the exact same moment, across the street, a founder is staring at their pinecone bill and wondering how it got so high. It feels like two completely different worlds, right? But here's the thing. They are both getting slammed by the exact same, incredibly expensive problem.
And that problem has a name. It's called the geometry tax. Think of it like an invisible surcharge that gets added to almost every single AI operation. And trust me, once you see it, you are going to start seeing it everywhere.
So what exactly is this tax? Well, what if I told you that most of those 768 numbers in a standard AI vector are just expensive baggage? What if, and this is based on some fascinating open-source research, you could pack all of the important information into just 32 numbers just by using a different mathematical shape?
But before we get into the nitty-gritty of the how, we need to understand the why. Why does this matter so much? And the answer is simple: money. Staggering amounts of it. So let's put some hard numbers on the pain this is causing across the entire industry.
So let's start at the absolute top of the food chain, Google. Projections suggest they're on a path to spend an eye-watering $75 billion on AI infrastructure in 2025 alone. A huge slice of that pie is going directly to storing and comparing these gigantic, high-dimensional vectors. And look, it is not just Google, not by a long shot. The whole industry has committed over $1 trillion to this arms race. When you're playing with numbers that big, even a tiny, fractional inefficiency becomes a multi-billion-dollar line item.
Now, okay, hyperscalers are one thing. But what does this mean for, the rest of us? Let's take a mid-market company. Say you're managing about 100 million vectors. With the standard approach, that's going to run you somewhere between $1,500 and $3,000 a month. With this compressed approach, you could get that down to under $200. That's not just a saving, that's a 90+% reduction. It's a total game changer.
And this is what that looks like in terms of sheer data. You're going from 300 gigabytes, which needs a real server, all the way down to less than 13 gigs. You could practically fit that on a thumb drive. It fundamentally rewrites your entire hardware equation.
And I really need to hammer this point home. This is not optimization. We are not talking about shaving off 10% or 20% with some clever new algorithm. This is a fundamental change in the mathematical substrate we are all building on. It's like switching from building on sand to building on solid granite.
Okay, so why? Why has the standard method been so inefficient this whole time? Well, it all comes down to a fundamental mismatch between the shape of our data and the shape of our math. Think of it this way. Language, ideas, concepts, they're all hierarchical. They're like a branching tree. But for years, we've been trying to force that sprawling tree into a flat, square box. That's Euclidean space. The only way to make it fit without completely crushing the branches is to make the box absolutely enormous. That's your 768 dimensions. But what if you had a container that was already shaped like a tree? That's hyperbolic space. It's curved, it grows exponentially, it's the perfect shape for the job. And because it's the right shape, you only need a tiny one, just 32 dimensions, to hold the exact same information. And that, right there, is the geometry tax. It's every extra dollar you are spending on compute, every extra gigabyte of storage, every extra joule of energy, just because you're using a giant, inefficient flat box when you should be using a perfectly shaped curved one.
So if that's the problem, what does the solution actually look like in practice? Well, when you fix this geometric mismatch, the results are, well, they're pretty staggering.
First, you get a 24 times compression ratio. That's what happens when you go from 768 dimensions down to 32. It's 24 times less data to represent the exact same core idea.
Now, the immediate question from anyone technical is, okay, what's the catch? How much quality do I lose? And the answer, at least on the standard industry benchmarks, is almost none. The research shows 97.4% semantic retention.
So you put those two things together, 24x compression with nearly perfect performance, and you get the real business outcome, a potential cost reduction of over 90% on your vector infrastructure. And that translates into real-world wins across your entire stack. your query speed gets a massive boost because there are literally 24 times fewer numbers to compare for every search. Latency plummets from the millisecond range to sub-millisecond, which unlocks completely new, real-time applications. And of course, less data and less math means way less energy. This structurally lowers your cost of goods sold for every single AI feature you ship.
Now, I know every CTO and engineer watching this is thinking the same thing. This sounds way too good to be true, and you know what? That's a fair reaction. So let's talk about validation, because the people who did this research actually designed it with skeptics in mind.
The framework actually comes with its own built-in Skeptics Toolkit. It's 3 specific tests you can run to prove to yourself that it's working. F1 is basically a math check. Is the new compressed data still sound? F2 is the common sense check. Does it still know that king is closer to queen than it is to cabbage? And F3 is a neighborhood check. Are the concepts that were neighbors before still neighbors now? It's basically a built-in BS detector.
And this is the part that I think is so brilliant. Most new methods are a black box. They just tell you why they're great. This one is totally transparent. It gives you the tools to detect precisely when and how it fails. That's the hallmark of real, rigorous science.
So in that spirit of transparency, we have to be upfront about the limitations. That 97.4% retention number, that's on general text similarity tasks. If you're working in a highly specialized field like legal or medical data, it's completely untested and would need your own validation. Also, the hyperbolic math itself is a bit more complex, so even though you're doing 24 times fewer operations, each one might be a bit heavier. You have to benchmark on your own hardware to know the true speed gains.
So what's the takeaway here? This isn't just an interesting academic paper. This is a potential strategic advantage. It's a competitive moat that's sitting there, available to anyone who's willing to question the industry's default settings.
Let me leave you with this final thought. We spend so much time and energy chasing bigger models and more data, but what if the most expensive, most inefficient part of our entire AI stack has been the one thing we never even thought to question? The geometry itself.
And the best part is, this isn't some proprietary product pitch. It's all open source. The code, the papers, that Skeptics Toolkit, it's all on GitHub right now, ready for you to test and validate on your own data. The question is no longer, is this possible? The question now is, who's going to take advantage of it first?